2,955?
Yeah.
And how many million are we going to do that by?
5.
5 million. All right. Hey folks, welcome out there to Mathline. We're so glad to have you with us this afternoon. I'm your host for this afternoon's session, Ernie Roberts. And this is what we call specialized segments. Specialized segments because we're going to take our whole show and devote it to a type of a segment of the math world, all right? And what do? We let you get pencil, paper, calculator if you feel necessary, and we're going to work some problems together, all right? Let you sit back, relax, we'll do some math, you do some math. It's a good afternoon way to go, all right? And I know some of you tune in through YouTube, and this is a great way to practice because we hit the same topic quite a bit, all right? It's a chance to practice, a little drilling, but also hopefully get a good understanding of what the concept is that we're going to deal with today. That's specialized segments in a nutshell. Let's see what our topic for the day is that we're going to specialize in. A few more 30, 60, 90 moments. Now, those of you who've been with us on these segments, you know we've been hitting these kind of things a long time. And you say, well, and some of you are new to it right now. You say, what is 30, 60, 90? It is a right triangle, and the 30 and the 60 and the 90 stand for degree measures, all right? So let's take a look. Let's take a look at how this picture is going to pan out. We've got a 30, 60, 90 degree triangle right here. And folks, because it's a 90, it makes it a right triangle. That's the first thing we notice. That's the first thing we notice. And that was a nice right angle. I agree, don't you think? I agree. Well, let's see what else is happening. I have a 30-degree angle. Well, I chose that because it's a little bit smaller up there. And down here we've got the 60. We'll choose it because it's the medium size. And then you got the right angle, which is the big piece. Now, when we look at a 30, 60, 90-degree triangle, we notice that all three sides have different lengths. And that's what this is going to be about. It says, given a 30, 60, 90-degree triangle, how do you know the relationships in the lengths of the sides hold true? And many of you are going like, oh, what are the lengths of the sides? What is the relation? What are you talking about? So let's see. First of all, letter C, let's put that in there. C is going to be our hypotenuse because we think of that a squared plus b squared equals c squared. Let it ride, all right? And since A comes first in the alphabet, I'm going to let it be the side opposite our 30. And then we got one more guy to go. The B, we'll put it in the middle because 60 degrees has B, and I say in the middle. It's not exactly in the middle between C and A, but it's somewhere running around in there. And we're going to talk about that relationship. How do we get there? And because all 30, 60, 90-degree triangles behave the same way, we have some great little formulas, all right? First formula. The relationship between the hypotenuse and the smaller leg. Smaller leg is A, right? Remember, how did we know that? Again, opposite the 30. Opposite means all the way across. Was B? B is our middle guy here. He's across from the 60. The 60-degree angle is the middle, all right? Or the medium angle, the middle angle, exactly, 30, 60, 90, right? So we're going to have 2A for our C value there because that's what we said. It's you multiply that small piece times 2, you get to the long piece. The hypotenuse, we call it. How about little old b over here? B has also this kind of crazy relationship with A and a square root of 3. So what we want to do is go back and figure out where did these actually come from. Now, we've done that in a previous show. It's been a long time. And I know a lot of times people pick us up time to time and so forth. I want you to know why these formulas work because, you know, it makes sense to know why you're using them. Then you can use them, all right? Then you go with it. So what we're going to do, we're going to play with this figure a little bit. We're going to pretend that we have a reflecting mirror going right down the middle here. All right, this line segment B is going to be like a mirror. And you can think of a line that includes that segment B, all right? When we're reflecting, when you look in the mirror, you get the reflection, right? So let's create a reflection. First of all, easy way to do this is figure out how long is it for A. According to this, I've got about 3.4 centimeters. So I'm going to go out here and extend from that point where the right angle is. We're going to go about 3.4 centimeters and hope this works. Well, it has to work, doesn't it? It's on Mathline. But right there's our point. And we're going to connect. We're going to connect the right angle vertex here and that point right there. And that is our, and by the way, they're congruent. So it's also an A. It's also an A, right? Let's connect our last remaining piece here. And we want to make sure we get that right. We got a new C, right? We got an hypotenuse C here. And also our angles have reflected over. So we have a right angle right here. We have 60 degrees right there. And we have a 30 at the top. Now, folks, those are congruent. Those are congruent. B is congruent to itself. A and A, well, goodness, we got two congruent triangles. The yellow one and the white one are congruent. They are congruent. So if we'll take this away for a minute, we're going to show you how this becomes those formulas, all right? So let's go back. Let's see what we got here. We got two yellow triangles, the same ones. Okay, we just filled in the other one. Magic, I know. So what are we going to look for again? We said something to the effect that C equal to 2A. We want to show you that works. Because once we do that, the B equals A times the square root of 3 will make an awful lot more sense, all right, where it came from. And again, right triangles, that's important. Put our letters back on there. There's B. Here's our 60. Here's our 60. We got A and A, remember that. Also, let's see. I've got something going on in that base down there, don't I? You certainly know that with this being C and C, we have an isosceles triangle for sure. All right, those two marks are there. But you know what else we have? We have 30 and 30, which add up to, you got it, 60. We got 60 and 60, three 60s, ding, 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 ding. Let's think about it. Equiangular, which also means we have what? Equilateral triangle. So this little curve thing I put down here is actually also, we're talking about the length from point to point. It's also C. Why? Because equilateral. They're all the same length. So if these two are C, the third guy is C. I'll put a little tick mark on that so we know we're talking about the whole bottom being equal to C. All right? And it's also equal to the rest of those sides in terms of the measurement, the lengths. Congruent. We like that word. We like that word, congruent. Notice we have 60s and we have 60s here. So again, that definitely cues in that we have equilateral triangle situations. But what I want you to really notice is right here, we have A plus A. Oh my goodness. When was the last time you thought you were ever going to say 1 plus 1 equals? Not 1. 2. There's 2A right there. And that's where this formula comes from. It just popped right out, didn't it? C equals A plus A, which equals 2A. So there's your formula. Boy, that was easy. Once we got through all the drawings and all the reflecting and all the thinking, it wasn't that much thinking, was it? Because once you figured out, oh, we've got equilateral, it all fits. Now, here's the story. Let's go back to A, B, and C. We now know A is A. That's pretty straightforward. We also have figured out that C is equal to 2A. So we've got two elements in place. We've got the short leg and the hypotenuse. Let's go for the longer leg there, all right? You say, well, where are we going to, Ernie? We're going to go to our good old friend Pythagoras and his theorem is what we're going to do. A squared plus B squared equals C squared. Good old friend, Pythagorean theorem. You say, oh my goodness, that's right, it's a right triangle. Right, it's a right triangle. You got it, yes, all right. Now, where are we going to go? Where are we going to go? We're going to change out the C and put 2A in its place. So we get A squared plus B squared equals, put in parentheses, and let me tell you why. If you don't put in parentheses, it does not give you what you're supposed to get. You say, what? What? Yes. Let's look. Because what is 2A times 2A? It's not 2A squared, it's what? 2 times 2 is, you got it, 4. So here we go, 4, and we do have an A squared because that A picks up the square exponent, all right? The 2, that little 2 has to come along for the ride. Now over on the left, nothing's happening yet. About to happen. We got A squared plus B squared equals, 4A squared. Does everybody see that? We basically did a nice little replacement, a substitution. We've already figured out C equals 2A. No matter how we stack it, it's equal to 2A. So, what are we going to go with? We're going to figure out what is B. So get B by itself. A squared is messing us up right now. So let's move it. Let's subtract. It's ready to move. And that's like a 1A squared, my friends. It's a 1A squared. Don't lose. Don't lose. Oh, goodness. I just saw somebody losing their A squareds out there. Don't lose it. You're not going to have just a 4. Actually, you're going to have, well, let's see what you're going to have. You have B squared equaling not 4, but what? Oh, my goodness, it's going to be 3. 3a squared, and we're ready to finish. Square root both of those. I've got b squared equals what? 3a squared? Is that right? That's right. Everybody got that so far? Let's square root. Now, things happen. We know the square root of b squared. In case you don't, it's b. On the other side of the picture, I have a squared. If I take its square root, that's easy. I get a. But 3 doesn't go anywhere. It's not a perfect square. It's irrational when I try to figure out what the square root of 3 is. So here's what we're going to do. We're going to bring that a squared, its root is a. We're going to bring the a out. We'll keep it positive, by the way, because this is a length. So we have to keep the positive length there. It's not a plus or minus moment here. And then we got the square root of 3. That, friends, is how we got those two relationships. It's Pythagorean, it's equilateral, it's geometry. It is just great geometry. Now you say, well, Ernie, why have you spent so much time on this thing? Because it's important to understand where it's coming from. And when you get into your pre-calculus classes, as well as doing the geometry, which is where this comes into play, it's in the high school geometry pretty much, you're going to be needing the 30, 60, 90 relationships to get through your unit circle, your pre-calculus trigonometry basics. Oh my goodness, it's fundamental. It's fundamental. So the more you work at this, the more you know about it, the easier it's going to come, I guarantee you, on down the road when you get into those senior years, junior years, honors pre-calculus, regular pre-calculus, all those things, and your trig. All right, so just keep that in mind. Keep that in mind. So let's do a quick little problem with it. And we're not going to prove anything much here. We're just going to go to the formulas and run them. It says find the perimeter and the area of the triangle if the hypotenuse measures 12. So let's go with it. We know hypotenuse. There it is. If this is 60, you got it. We got 30 down here. All right, let's go. Let's go. Well, what do we do? What do we do? Formula, formula. We start with a hypotenuse this time instead of the shorter leg, right? But here's A. There's B. Watch and see. Watch and see. So we said it takes 2 A's to make a C, right? That's interesting. 2 A's to make a C. In a 30, 60, 90, it does. So let's think about it, take half. That means we're going to have 6. Once again, that comes from that formula. C equals 2 times A. Or, if you like A equals, you can just make it 1/2 of the hypotenuse. All right? That's where we go. So we're 6. These are meters, so we could put M's on them for fun. All right? Now, let's see where we're going. We're not going to C, we're going to B, right? So here is B. Use that formula. A times the square root of 3. A is 6. So B is equal to 6 times the square root of 3. We like radical form, so we're going to leave it there. We're going to keep it in radical form. However, you always love that when I say however. That's not that bad. If you were wanting it to the nearest hundredth, just multiply on your calculator. 6 times the square root of 3, it will give you something. Remember, the square root of 3, because it is irrational, it rambles on and on and on. So when you multiply by rambling on and on and on, you're going to get more rambling on and on and on. And rounding off will become important, because otherwise you're going like, do I have 10 decimal places? No, you actually have infinite decimal places. You just only had 10 the calculator gave you. So round it off to whatever, the hundredths, tenths, nearest, whatever it says for you to do. That's your problem status. You need to read carefully, right? And in this case, we're using radical form, on radical form. So let's apply it a little bit. We brought in that equilateral triangle a little bit earlier. Let's go back to it. Let's go back to it. Now, I have a side of 12 inches. That's delightful. It's equilateral, so I don't have one side. I have 3 sides. I'll just put them all in there just because we like that. And here's what happens in an equilateral triangle. We're looking for the altitude. Now, some of you are going like, altitude, what does that mean? That means we're looking for, from a vertex, we're going to make a perpendicular. And I'm going to guesstimate here, all right? We're going to guesstimate best we can. Drop it right there. Here we go, here we go. And it's going to split this guy and that guy in half. That's what altitudes do. And by the way, altitudes are perpendicular. They make right angles. We can go on and on and on. And guess what you've just decided? We have 60s. We had 60s. Now we have 30s. 30, 60, 90. Here's the application. Equilateral triangle. Are you ready to rock and roll? Let's rock and roll. Half of 12. This sounds like the problem we just did, isn't it? It's just a different look. It's just a different look. So here we have 6 split in half. Think you can do that mentally? Yes, you can. Again, those who forgot the formula, is because 2 times A gets us where we're going. To get to B, A times that lovely square root of 3. That's irrational, so we leave it in radical form. And here we go, 6 times the square root of 3. Now the question says, find the altitude length. Where's the altitude? It's this little guy that's opposite the 60 in this problem, all right? There it is. There's your altitude, and we can put a little bit of a 6 square roots of 3 inches. There's your altitude. And again, easy stuff. That's your B. That's your B in that ABC situation. Remember, opposite the 30, take half. To get to this one, you're going to have to multiply that A value, or that smaller leg, that shorter leg, by the square root of 3. And then you've got what you're looking for. You got everything you need. I could ask for perimeter. Did I ask for area? Not yet, but I guarantee it'll probably happen somewhere else here soon, all right? In fact, let's go back to that problem which I just went through, and if we can go away with just a second, because I got so excited about finding B, we didn't get to the answer to the problem, did we? Let's take a look at that problem one more time here, because I was thinking there's a perimeter and area somewhere out there waiting for me. And there it is. So let's do that perimeter, all right? You got it? It is A plus B plus C. Now some of you are noticing, and I hope all of you are noticing, you've got 6 plus 12. Ooh. And then you got that 6 times the square root of 3 mess coming up. So Ernie, can we go play the calculator game? Yes, we could, but we're going to keep it in radical form, all right? We're going to keep it in radical form, which means we're going to add the 6 and the 12 together, which is going to give us 18. And we're going to leave that separated because this got a square root of 3. The other guys do not. And that, my friends, that is your perimeter in meters. Not square meters, but meters, all right? There we have it. Let's go to the other side, finding the area. 1/2. Okay, how do we find area of a right triangle? We take the altitude times the base, and by the way, both of these actually are altitudes of the right triangle because they make a right angle. So you can interchange them. Since A is on there for altitude, it's going up high, we'll go with altitude. Base kind of going out there horizontal, we'll go with base. But it's 1/2 altitude times the base, sometimes known as base times height. All sorts of ways we can read it and say it, but it basically says we're going to take 1/2 of our A value, which is that vertical, times the horizontal, because they make right angles together. That's why they're altitude-based relationship. And we're going to multiply, and we're going to have square meters when it's all said and done. How about it? Let's take half of 6. That'll give us 3. Then 3 times 6 square roots of 3. 6 times square root of 3, and we're going to say half of 6, which is 3. That sounds like 18 to me. Whatever you do, don't mess with that square root of 3. It's already nasty enough. It goes along for the ride when we multiply, all right? Just like here, it stays on its own. Now, if you want to go and figure it out, go to your calculator and multiply it out, round it off to the nearest hundredth or something like that. That's fine. But this is where we are ending up, and this time we are in the land of square meters. That's our story, all right? So I want to make sure we understand where these numbers are coming from. And that, again, is kind of the area. And that we just did with the equilateral triangle. Let's come back and do one more equilateral triangle problem. This time, let's show the world we can switch gears. Ooh, we always hate that. Change is just kind of scary, isn't it? Let's see how we're going to do that. We have an altitude. I didn't draw one in, did I? So we need to supply one. Remember how it works? It comes from the vertex down perpendicular to the opposite side. There are 3 of them, by the way. We could have run it from this vertex out there, but it's kind of nice to see it come down vertically, all right, and meet a horizontal base, although we aren't always going to be blessed with that situation. So where are we going to go? We're going to put a 12 right here because that's the altitude. I don't know anything else. So we're going to look for perimeter and we're going to look for area. Let's see if I can remember to do both of them, right? Let's see what we got going here. First of all, it's equilateral, so I know there's some 60s lurking. And there's a 60 waiting to be divided at the top. These are degrees, by the way, all degrees. Right angles, 30, 60, 90s, rock and roll. And we go to, oh, wow. You didn't start with a hypotenuse. No, I guess I didn't, did I? You didn't start with a shorter leg. Ugh. You started with the one in the middle, so to speak. What are we going to do? We're going to use a formula. The formula says B is equal to A, which is our shorter leg, times the square root of 3. Now you say, well, how's that going to help us? Because this is B. We know B. So put a 12 in there. This is A, as is this little piece. So when we figure out one of these A's, we're going to double it and have a whole side of the triangle, which is going to lead us to perimeter. So sweet. So sweet. Let's see what happens. Uh-oh. There's always an uh-oh, isn't there? Next thing we've got to worry about is, how do we get A by itself? That says A times this crazy radical square root of 3. We would like to have A by itself. That means we got to divide both sides by that crazy radical square root of 3. So let's do it. Nothing better than just do it, right? No, Nike is not sponsoring me today. We have square roots of 3 going away. We need to worry about what to do because we do not want a square root of 3 hanging out in the denominator. Radicals are not allowed in the denominator. You say, really? Really, they aren't. I'm not always sure why we go there, but it's been a tradition, all right? And it makes it a little more interesting. It's a little technique we call rationalizing the denominator. So let's do that. We've got 12 divided by, that's what that means, yep, over the square root of 3. Well, we might get it back here if we'll drop the bottom out of there, guys. Thank you. And we have to get rid of that. And if you remember, the technique is to multiply it times itself. The square root of 3 times the square root of 3 gives us 3. On top, we have 12 times the square root of 3. Please do not make that the square root of 36. Doesn't work that way. The 12 comes along, meets up with the root of 3, and they go along for the ride together. They do not mix and become a 36 in any size, shape, or form. However, these two little guys down here are like coming to be a square root of 9. They're both under the radical, and we know the square root of 9 is going to give us 3. So the deal is, if we multiply a square root times itself, say goodbye to the radical. Say goodbye to the square root symbol and keep the number that's under it. At this point, we're ready to finish, aren't we? We're getting close. How about it? 4 times the square root of 3. That is this little guy right here. Now let's play around. Here is also 4 times the square root of 3. Together at last, what are they going to give us? 8. Count it. 4 plus 4 gives us 8 square roots of 3. So here we go. 8 square roots of 3 here, 8 square roots of 3 there. It did ask for perimeter. We're not going to forget that this time. Oh, we can put them all together this time, my friends, because they all have square roots of 3 attached. So I got 8, and 8, and 8. That gives us a perimeter of 24 square roots of 3. Now, if you want to get technical, hit that calculator and find out what the square root of 3 is. Multiply it times 24, and you can take it down to good old round off, in this case, inches. All right, so we're going to put a little inches right there. That's the perimeter. What is the area? The area, once again, that formula for a triangle. We're going to look at the whole big triangle here. Area equals 1/2 base times height, or altitude times, in this case, we're going to be looking at a base of 8 square roots of 3. So let's put it in there, 1/2. We'll put the 8 square roots of 3 right there, happy camper. And the height, we said, oh, we started off with that, right? It was given to us. So we got 12. They're inches, so they're going to become square inches when all's said and done. Let's clean this thing up. It's kind of messy, doesn't it? It's almost off the page. That's how close we're getting. So hey, how about it? Let's go 1/2 of 12. That's easy. That's 6. 6 times 8 square roots of 3. I think 6 times 8 is 48. Don't tell me later if I'm right. Of course I am. Not always am I. Sometimes I guess those are a little bit confused. But those times tables are important to know. And the square root of 3, it comes along for the ride. And folks, these are, once again, square inches. Square inches, there you have it. Now, what goes on here? Again, area in square inches. This was just little o inches, sorry, that's all we could do. But notice the tricks, the things you got to be able to do. Be able to multiply by square roots, or in this case, divide by square roots. Know when to keep it, know when to lose it. Whew, lots of stuff to go on there, isn't it? That's why these programs are so good and great for review. They're going to review your radicals with you. They're also going to review the rules of the 30, 60, 90, and on top of that, get you ready a little bit for that pre-calculus coming up ahead. When you start working with what they call the unit circle and you see square roots of 3s and square roots of 2s, we're going to come back and review all of those next time on our next Mathline Specialized Segments. And again, remember, you can catch this show sometime down the line on YouTube. And we also love it when you like us on Facebook. And of course, we'll be live again next week.